All right, this is Math 31, 3.3, Part 2. Definitely probably not worth it to split these into parts. This is a relatively short part here. We're just going to talk about the applications to biology. And I think what's really important is that just like the applications to the natural sciences, we talked about linear density before, applications to physics, it's really the same concept that average rates of change are secant lines, and we can just use our slope formula for that. And then instantaneous rates of change are tangent lines, and we need to use our derivative for that. Now, if you really wanted to, you could use, Formula 1 or Formula 2 to find the tangent. But now that we've, maybe unlocked isn't the right word, but now that we know the power rule and the quotient rule and the product rule and the chain rule, we are able to, exploit those things and do these a little bit simpler for sure. So this question asks or tells us that the population of bacteria after T hours is given by N equals 500 plus 200T plus 12T squared. It wants us to find the average rate of growth from 2 to 4 hours, and then the instantaneous rate of change or instantaneous rate of growth, same thing, after 5 hours. So the average growth from 2 to 4 hours, and I'm just going to write that as an interval, that we are trying to find the growth from T being less than or equal to 4 and greater than or equal to 2. And that's going to guide us to our slope formula. And we're going to say that the change in the bacteria with respect to the change in time is going to be our function. And we didn't really have a function notation here, so I'm just going to replace this with N of T so we can talk about this. And we are going to look at the number of bacteria at 4 hours minus the number of bacteria at 2 hours, and then divide that by the time interval, which is 4 minus 2. You certainly are more than capable of evaluating polynomials, so we're going to cheat here, and we're going to say that that's 1492 minus 948 divided by 2, and what that yields is 272. And I'm going to put the unit here. That's going to be bacteria per hour. And you can find that in how they identify the variables. They tell us that the population of a bacteria, that's N, is given after T hours. So if we picture this as delta N over delta T, which is written over here, I think it's important that this is, dN over dt. Right? That's that Leibniz notation is showing us the same thing. The difference here is that this is occurring over a time interval, whereas the second part of the question wants us to determine dN over dt when t is equal to 5. And essentially what that is how quickly are the bacteria growing or decaying, if that was the case, at the 5th hour. And a lot of students have this misconception that bacteria grow at a constant rate. Typically that growth is exponential, and it can depend on the amount of food, the amount of space. That exponential growth won't happen forever. But we can find and maybe exploit the fact that it's a maximum at this temperature and this much food or something along those lines. So in order to do this, we have to find dN over dt. So if I know that N is equal to 500 plus 200T plus 12T squared, then I hope logically, after you've done a couple of these with those implicit differentiations, that dN over dt, so the derivative of 500 is 0, it's a constant. The derivative of 200T is 200, and the derivative of 12T squared is 24T. Now that's our general derivative for the function n. We want to know dN over dt when t is equal to 5, and that's as simple as substitution. When I evaluate that expression, I end up with 320, and the unit is actually going to be the same. It's still bacteria per hour. And the reason why maybe this growth is increasing, right? From 2 to 4 hours, we only had 272. At 5 hours, we have 320. It is really what that is trying to show, or at least what that is showing, is that the more bacteria we have, the quicker that bacteria grows. And that is something that we looked at in 30-1 when we talked about exponential growth. And we're going to continue to connect that in calculus and talk about concavities of graphs, and how if the derivative is changing, the second derivative can give us that information. Okay, that's the end of 3.3. Make sure you do check those digital notes for the homework, and then you can self-assess.